Okay, I'm Demian Martin. I've been playing with audio for too many years, and this sort of started out because I had all of this test experience and experience measuring distortion, and thought I would go share some information about how to measure distortion. Certainly not at the super professional level where you're spending a whole lot of money and living and breathing it, but how to just get up on the air to do it. So the first phase was that we would go and just sort of demonstrate what distortion is. And Jonathan contacted me and I said, great, because he has some demonstrations to show distortion. I come from originally spectral audio, and then through a whole chain, I've been working for the last 15 to 20 years with Monster. So I have a lot of experience at that level, and as well as working for a number of other clients doing high-end audio. And meanwhile, Jonathan comes from an experience in the test equipment realm doing all kinds of test equipment, including audio precision. So at this point, I can hand it off to him.
Okay, so I'm Jonathan Novick. I've been selling audio test equipment for the last 15 years. I was Audio Precision. You all know who Audio Precision is? Most of you? Yeah. So I was their top sales guy for most of my career at Audio Precision. I always had a background in audio, but before that I was with Hewlett-Packard Agilent for 16 years, and before that I was a design engineer, and my specialty was RF and microwave stuff. So, but waves are waves, and measurement is measurement, and good measurement technique goes everywhere. And when I joined AP, I pretty much expected I was going to find a lot of people that were going to teach me about measurement and design, because these guys living and breathing it. And I was surprised how often I got the question, what should I be measuring? And I'd see people look at results, and they'd been users of AP gear for 20 years, and they'd look at the results and kind of go, I'm not sure what this is telling me. And wow, there's a lot of need for some basic stuff. And so we're going to start out with what is distortion. There are two types of distortion. There's linear and nonlinear. Linear distortion is something that doesn't add new harmonic content to your signal. So if you're doing change of frequency response, you can look at as a type of distortion, but it's not going to add different harmonic content. Gain, just flat gain, is a type of distortion. The signal came in at one level, left at a different level. So the difference between the output and the input is distortion. So you can say gain is a type of distortion, but it doesn't add spectral content. Nonlinear distortion is anything that will add spectral content. You've all heard the term total harmonic distortion. That's distortion measured with a single sine wave. There's also something called intermodulation distortion. That's something when you use multiple sine waves. There are two numbers that you commonly see, THD and THD plus N. It's very important to know the difference, because one just looks at harmonics, and there's things that are related to the quality of the sound that is not harmonically related, but shows up in a measurement, and that's THD plus N. Normally, you're measuring this, but sometimes when you want to find out what your system is doing, you want to measure the other. So as I said, linear and nonlinear, kind of covered this. Clipping, slewing, intermods, crossover distortion, all that stuff is examples of nonlinear distortion because you're adding spectral content. So I'm just going to quickly here play some tones out of my little 3-inch speaker here that's going to create its out of the computer, which is going to create some distortion, through a little 3-inch speaker with the volume cranked way up. So I'll play you as pure tone as I can. Yeah, and it's clipping, but you can see it's mostly a single tone here. And okay, that's better. But let's go on. And now I'll play with second harmonic content. And with third harmonic content. By the way, I made these files so that they all have the exact same amount of distortion. This is all 7% or minus 23 dB THD. So you can hear that already. We listened to the second harmonic and third harmonic. They sounded different, but if you're just looking at the number is the same. Now, what if you have a spurious tone, like an alias tone or something like that? This gets really bad. That's going to sound bad. But if you're just looking at a distortion number, you don't know what that number means. What about AC hum? Okay, so you can hear that. Again, it's all 7% distortion. Very different. The numbers aren't telling you what's going on beneath. Some noise in there. Same measurement. And now this one's not going to come out very well on this system, but crossover distortion. You can hear it's not the pure tone. Crossover distortion is actually very audible at lower levels, and this is a fairly high level, but it's still, all those, if you were just looking at the measurement of THD plus N, you would see 7% on all of those. Now, if you look at the second harmonic, the third harmonic, both of those would show a 7% THD. The other ones would show almost no THD because the extra content wasn't harmonically related. So the takeaways from this, when you get an older analyzer, they're all measuring THD plus N because the way they're designed, it is easy to notch out. Most analyzers are notch analyzers. So it's easy to notch out the single pure tone. And what you see is everything else. When you get to the DSP analyzers, you can get some insight. You can see the spectral content that's in your waveform. So the issue is, and this is why the industry's kind of, I think, gone down this road, is if you can't tell what kind of distortion you're generating, you have to have some really low numbers. You're chasing that low number just because you don't know. But if it's low enough, you're not going to hear any of it. So, but you know, especially when you're doing tube amps and stuff, a little bit of second harmonic distortion actually makes it sound a little bit fuller. It's kind of a warm sound, as people call it. So that's the takeaway here. And the reason why I put this in this presentation, because this is really about what are your low-cost solutions out there for doing measurements. And of course, buying old gear on eBay is one of the lowest cost solutions. But a lot of the old gear is analog gear with notch filter design, and you can get a number, but you can't get the insight necessarily. So I'll turn this over to you now. And there are different types of analyzers. Just there's the used equipment, there's the professional equipment, and the SOUNDCARD equipment. And let me just finish this one. The used analyzers, when I was at AP, my #1 competitor was eBay. It was the old System 1s that were on eBay. And it's hard, you know, if someone was buying an old Rode and Schwartz, I can make fun of them up the wazoo, but if they were buying a used AP, if I dissed the old AP, I may piss off the founder of AP, so that's probably not a good idea. But really, it was my #1 competitor. I lost more sales to that than to any other competitor out there. The problem with it is parts availability. You know, anything with old gear, you're probably all familiar with those. Finding the schematics, finding the parts, and things like that. And operating system support for computer-controlled gear. And the feature sets, you don't get a lot of the old equipment doesn't have the DSP capability. Trying to get printed data out of old gear is a really big problem. And that's where a lot of people give up on it. It's like, okay, I got the number, I can't get a graph. And especially if you're working as a consultant or some people want to see the pictures. So that's where these things kind of give up. All right, now I'll turn it over.
Oh, okay, I'm going to see if I can figure out how to operate this thing.
Forward back.
Okay. Okay, so forward. So traditional analog distortion meters, analyzers, these are the things that have been around for many years. You've seen them. Probably the most common traditional one is the HP 334, but they're all based on a notch filter. If you start out with a bag of analog parts, the easiest thing to do is to make a sharp notch filter, make it tunable, and then you measure what's left over. You basically measure what's coming in, and then the ratio of that to what's coming out is your distortion number. That's why in the previous presentation where he shows the hum versus the second harmonic, third harmonic, they all give you the same number because this instrument can't tell them apart. All it does is see everything that's left over after you remove what went in. It's a valid thing to do, but it doesn't give you the insight you need if you're trying to make something better. All you do is sort of poke around in the dark until you find it. The other types of analyzers, it's traditional analog distortion meters, but these types of analysis survive today. The second type is a cancellation, where you take your input signal and the output signal of an amplifier. You adjust the output to match the level and the phase of the input so it cancels, and whatever's left, again, is the nonlinearity of the amplifier or noise or whatever it adds. This has also been used for a very long time. And then the third option, and this also goes back, is the manual spectrum analyzer, called a wave analyzer in the old days. And this is an instrument where you would literally, you'd measure the fundamental, and then you'd tune it up and measure the amplitude of each harmonic, manually finding it and writing it down, and then doing a lot of manual calculations. So if we go forward, here's the traditional notch filter analyzer. This thing has got to be from the 30s, as you can tell. They really haven't changed a whole lot from this design. These were very common in radio stations because the FCC required that you test the performance of your transmitter. And the requirement was to get below, I think it was 3% distortion. And that was from the 30s even. This one, this is a real rare beast. This is RCA's, again from the late 30s. This thing is all about cancellation. This is, as I was describing, you take the input signal, the output, and the output signal, and try not to get that noise. It's got a lot of little adjustments here so you can adjust the phase, because you have to have a phase match to get a proper cancellation. You invert the signal, you match the phase, and then you can remove it to a pretty high degree. And then this, and I actually had one of these, literally you tune it. It's like a radio receiver. You tune it from frequency to frequency and measure the amplitude at each one of the critical harmonics in the fundamental, and then you do the paperwork cancellation. It's a fun instrument. That thing must have 30 tubes in it. And it's stable for about 15 minutes before you have to go readjust its internal tuning. But all these three principles exist today. Now, these are commercial instruments that do what we were just seeing, but they have a lot of things in the design to make them a lot easier to use. The top one there is a sound technology. Those have been very popular for many years. Pacific Stereo bought bunches of them for all of their stores because they actually offered service.
One thing about this, when you get to this generation, it actually had an oscillator built into the unit. Whereas some of the really early ones, you had to have a separate source. So this was a big convenience to have the oscillator. Huge convenience, plus they tuned to match the oscillator and the analyzer, so you didn't have a whole lot of fine tuning to worry about. The sound technology, the HP underneath it, which actually shared to some degree common origins because the sound technology people all came out of HP. The amber was made in Canada. It's actually a somewhat later instrument, but it's very similar to those two. It's actually a very good instrument once you get one tuned up, and you can even get a battery-powered version so you can get away from ground noises. But this is a generation. It's certainly suitable for a hobbyist if you have the patience to make them work. I'd warn you on the sound technology because the coupling between the oscillator and the analyzer is mechanical behind that huge array of push buttons. If something gets out of line there, you're in deep trouble.
Otherwise, they're fully maintainable and there's nothing terribly exotic in there. The most exotic thing are some optocouplers, and you can actually get improved optocouplers and improved op amps for them today. There are people who have modified the HP 339 there to get really good performance. And it's a perfectly valid instrument, except on all of them, the knobs disintegrate. Nobody's come up with a solution other than faking new knobs. Okay, next generation. Now we move to a much smarter instrument with a digital readout and often an internal microprocessor. The top one up there, the HP 8903, that was actually, I believe, originally targeted at an upgraded military requirement, so they made jillions of them. They're really pretty nice. They're not the easiest to work on, but they're pretty reliable. The A version doesn't have a fully differential input, so that can be a problem. You want to get the B version if you find one of those. There's information online about how to fix them, and it's certainly a valid instrument to get, but they're complicated. The one below it is the Boonton, and that exists because Boonton was losing sales to HP, so they went and created an equivalent product, and it's very equivalent. The circuitry is pretty similar, in fact. It's easier to work on, and there's information. I've even posted information on how to hot rod one of those. And then below that, we have the Tektronix AA501.
Which was designed by the guys that founded AP.
Exactly. There's a lot of history here. There aren't that many real threads to follow. And that's a very nice instrument. You have to have the mainframe to run it. Those two little things next to it are matching oscillators that come as part of the package if you buy the whole package, and you can do IM with it and all kinds of nice things. Again, it's mostly manual. The nice thing about it is it's automatic tuning. All of these guys have automatic tuning. Whatever the source is, whether it's internal or external, it will automatically tune to it and null it, so you can get a measurement without a lot of screwing around. And the last one there is kind of a rare beast. That's the Amber 5500. It's targeted at the same sort of marketplace as the other two. Those three instruments over there are all GPIB interfaceable, so you can hook them up into an automatic test system and do all kinds of great things with that. For most audio hobbyists, that's kind of irrelevant, but if you're in a manufacturing environment, that's actually more important than the knobs on the front, because you want to set up to go test all of your products efficiently, and if it's automated, then you don't have to go teach somebody how to turn all the knobs. Then we move over to the world of PC-controlled analyzers. The audio precision, that goes back to the mid-'80s. And it was actually a radical idea at the time, because when that thing was introduced, IBM PC was a rare beast, really.
It was also the first time you could actually see a frequency response curve.
Without manually plotting it on paper. Right. Yeah, those other instruments, if you had an XY plotter, you could plot it. That was real nuisance. Been there, done that, don't want to do it ever again. Okay, so we now have this computerized generation. The audio precision defined it. It has very high performance electronics. I mean, really good stuff, especially for the period it was in. And the computer interface gave it a lot of capabilities and a lot of efficiencies that you wouldn't get otherwise. But that first one is still from the era where it's essentially analog tuning inside and kind of an analog processing of the output. They introduced a version with DSP. He can probably provide more information on that later, because I don't know the specifics of when they introduced it, but it was the first time you could get a box like this that from internally, instead of having to manually plot the spectrum, it will give you a spectrum analysis so you suddenly know what the distortion is instead of the fact that you got distortion.
Well, what they did before they had the distortion capabilities, they put some filters in there. So there's a 400 hertz high pass filter. You put that in there, if your distortion drops, you know you had hum problems, because most of the hum issues are below 400. And so you could use different filters, analog filters, to try to see where your problem was, but you know, it was hokey.
To put it mildly. Below it, we have the Rhodian Schwartz. Those are kind of rare here. They're still quite expensive. What's different is they built the computer inside of it. The problem with any instrument like that is you're trapped by the computer that's in it. Upgrading to a newer guts is usually catastrophic. It doesn't matter if it's the Rhodian Schwartz. Tektronix sells oscilloscopes for $100,000 that within 4 years are essentially doorstops because they didn't migrate, you can't migrate them to a current operating system. It's very frustrating having had that experience. And then the bottom one there, that's the D-scope. And that's another example. It is computer interface. The computer does the bulk of the work. This has analog processing, digital conversion inside. I don't even know if that has any analog notch filters in it.
What?
Do you? The D-scope?
No, it's all DSP.
Okay, so it's all DSP, so whatever the ADC gets is the best you're going to get.
And it's a 15-year-old design that has not been updated. At least 15 years old.
Yeah, so I mean, the software for those is pretty decent. Everybody tells me it's great software, but if it's limited, 15 years ago you could get good ADCs, but it's still a limitation compared to where the performance is today.
It's about a System 1 level performance.
Yeah.
A little bit worse.
Yeah. So then there's the hobbyist approach. This dates back from the late 80s, early 90s. This is Bob Cordell's analyzer. These are the pictures I could find online. As you can see, you can build yourself a distortion analyzer. It's a wonderful project, but I would today put it on a par with building boats and bottles. It's a lot of work to get to where you want to be. There's an enormous number of parts and a lot of wiring and tuning to make that thing work. You can see the picture of that particular assembled unit. The other thing sitting down there is his distortion magnifier. Remember that RCA thing, the cancellation process? The distortion magnifier works on that principle where you take the input of the device, the output of the device, you do a subtraction with some careful tuning, and then what's left over is the distortion. The nice thing about the distortion magnifier is you can put it in front of a conventional distortion analyzer and it amplifies the sensitivity of the analyzer. It's a little bit complex to sort of follow it through, but the essential principle is the same as that ancient RCA device. And
the one thing with any of these cancellation type, these days, most electronics has a lot of DSP in there, and you've got a bunch of latency to deal with. So it's not just a phase error, it's a delay error. And so a lot of these cancellation approaches become a real
you can't use them.
To delay, especially like Bluetooth, 100 milliseconds of delay is not.
You can't. It's not possible. This works with an analog amplifier. You probably couldn't successfully use this even with a switching amplifier. Even those have too much delay to really dial out. Some are probably manageable just, but it's just not the right solution for that. Here is an IM analyzer, and this is another example of the kind of task it has been in the past if you want to build a high-performance analyzer and you want to build it yourself. This instrument is quite good. Actually, its residual is about a minus 120 dB, but that's all hand-wired. It's a huge project. If anybody's interested, I have all the documentation I'll share, but it'd probably take you 6 months to successfully build it. So that's where we are then. Sound cards. Before about 2004, 2005, sound cards were defined by the sound blaster. You got sound out of it, it can record sound. Its performance was not particularly good. In some cases, it was pretty mediocre. Half the things it said it did were a lie. So you really couldn't trust it for measurements. I mean, you'll get sound out of it, and it's important to understand. That's where the computer industry started, and their focus has never been perfect sound. It's always been no phone calls because the thing didn't work. They will compromise everything about it to make sure that they don't get a phone call because something didn't work. In most of the computer operations, if they got a phone call, they stopped making any profit on the product. So they'll do anything to compromise that. So that's why if you look at a typical computer sound card, It has sample rate conversion, AGC, filtering, equalization, all kinds of crap that will just really compromise what you're doing. So you want to be aware of that. And typical internal sound cards have variations on that. External sound cards work a lot better if they're selected right. I'm not sure where, does the next slide give me, yeah. So internal sound cards, again, work all the time as rule number one. There are some that are good. There was a short period there where the competition said we had to have a good sound card. That meant capabilities up to 192, 16-bit worth of actual accuracy, pretty decent signal to noise ratio, stereo line level inputs. That's important. At one point, the industry just sort of instantly morphed. So now they all look just like the headphone jack on your cell phone. They have one analog microphone level in that's very compromised and a stereo output, usually not terribly good. And for the industry, it's perfectly fine. So you can't really expect the sound interface on a desktop or a laptop from the last 5 to 10 years to be particularly good.
And clocking is an issue with those. They're not designed as high-performance instruments. You don't get a nice PLL in there to adjust your clock. So you can have a lot of errors on the capture side just because of jitter and things like that.
I've actually run into sound cards in full-fledged computers where the 44.1 was 44. It was that far off, way out of spec. But, you know, they derived that clock from something else and it was lots easier than making it right. So what you want to look for, if you're going to be doing this, you need a sound card that is of decent, recent generation, decent quality. You don't really want the home theater sound cards. Their primary focus has always been lots of output channels. 6 channels minimum, typically 8 channels, and now with Atmos taking off, we're going to find sound cards with 12 outputs, but just one stereo pair of inputs. And on many of the ones I've looked at, the output side will do 192.24, the input side stops at 96. And these are the kinds of compromises they make. They don't really expect you to do much with the analog input. So it's not been a high-level thing. The recording interfaces are what you're going to look for. They come in a whole variety. Currently, there are a number of decent ones you can find. EMU had a number of them. They were always distinguished by, among other things, being able to go up to 24/192. Their EMU Creative bought EMU, and that whole business kind of sat there and hasn't really had much energy put into it in nearly 10 years. So the stuff is old, the drivers can be buggy and drive you nuts. But the hardware is really pretty decent. The current fave and probably the best value is the Focusrite stuff. And I think I have a picture of one coming up. But in essence, the core thing, look at a product that was designed for people to do professional recording with. Don't look for an audio file. Okay, things you can find. Typically today there'll be a USB input external sound card. You can also get internal sound cards, which we'll touch on. ASIO is a nice feature. It allows you to work right around the internal Windows sound engine. Remember I mentioned that the sound engine is designed to make sure it always works, not that it's accurate. So you really want to work around that. In Windows 10, there are 3 places where it will engage a sample rate converter if you don't catch it. You have to look at the card interface, the software interface, and the internal sound engine. Each one of those will trigger a sample rate conversion. The native sample rate conversions in Windows are not very good. The reason for that, aside from the fact that you don't want sample rate conversion for measurement ever, but beyond that, good sample rate conversion is very processor intensive. Lousy sample rate conversion that's perfectly okay for a recorded voice is pretty simple, so that's what they put in. So avoid it if you can. Learn, if you have to use the sound engine, how to find all the places you set the sample rate and the bit depth to make sure they all match and you're not screwing around with it. If you use ASIO, it walks completely around that engine. The driver that talks to the card creates the data stream that the application connects to directly. It never touches the Windows sound engine. And that is preferred if you're doing it that way. On Apple, it's a whole different thing, and on Linux, it's yet another thing. Both of those are special cases. I don't think we want to get too wound up with that. As he says, no auto ranging on sound cards. You do have to understand the input level capabilities and limitations. A Pro Sound card is liable to be able to handle up to 10 volts RMS if you set it right. Typical home audio cards, maximum input is like 2 volts if you're lucky. So you need to be aware of that. It's very easy to damage these if you go too far. If you take a sound card, hook it to the output of your 50-watt amplifier, you'll probably have toast. So you have to manage that, and there are ways to do it. Okay, software. There are a lot of software options. I have a flyer over there that lists a number of them that are specific for actually measuring analog and digital electronics. There are acoustic ones, and there's electronic ones, and there are some that try to do both. But you can't count on the acoustic package being optimized for measuring the kinds of things you'd want to measure in an amplifier. And by the same token, packages that are designed specifically for measuring electronics don't work for acoustics because they can't relate to the fact that the sound is moving through space. So there are a number of them. With the software you can get today, you can do all the standard measurements just by pushing a button, and you can get a lot of information. The chart there, that is a spectrum of basically an oscillator. As you can see, the distortion is very low. You can see what it's made up of. There are all these little spikes down there. Those are either harmonics or spurious signals. And after a while, you'll be able to say, okay, those are harmonics. That is a spurious signal, and it's probably coming from, say, a USB interface, or there's this other power supply thing, or something that has to be fixed. It's very useful for understanding what's going on inside of the box. Now, the other caution, and I mentioned it here, if you're using a sound card analyzer and you're trying to find the optimum setting for a bias on an amplifier, it can be pretty agonizing because to make that plot takes a finite period of time. So you'll turn the knob and wait, and turn the trimmer and wait. It's not real fast. With the analog analyzer, the one thing you have is you turn the knob and the meter moves. So it is a thing to be aware of in terms of what you're trying to do. You can do it with this, it's just not as easy. In the handout, I think there's 11 or 12 different software options to go look at. They are all unique. They all represent what the software creator felt was important. And it matches up what he wanted to do, how he wanted to do it. You get it, you play with it, you decide whether or not it matches how you want to work. And it's not that any one is better than another. Some have a whole lot more capability and are much harder to use. Some work very differently from anything else. But once you learn how to use them, they're very powerful. I think the real key thing here is if you find one that does what you want to do and you can use it, just learn how to use it and live with it. Don't spend your time chasing them because you'll never be happy. I've been there. Okay, Pro sound cards. You can put a sound card inside of a desktop computer. Here I have at home a desktop computer inside of which I have a Lynx card, an RME card, and an EMU setup. Those are basically the three dominant options you'd have for you getting a sound card in a PC to do measurements. They're all very good cards. Each one has its strengths. Each one has its weaknesses. The RME has really good digital analysis capability. If you feed it a digital signal, it'll tell you all kinds of things that are hard to find out any other way. The RME's analog section is compromised a little bit compared to the other two. The Lynx has the best out-of-the-box analog performance of an audio sound card. The EMU, again, driver challenges, but otherwise it's very good. Also, there's information on the web about upgrading op amps and so forth to get better performance out of them. Any of those is going to set you back $300 to $500 to buy, but they are also very good recording interfaces. If you actually are a musician and recording yourself, these are all very valid solutions, and they are also have been used for many years in professional studios doing large volume professional production. They're not compromised. The user interface to drive them is a learning curve. It's as hard to learn as any of the analysis software, especially the EMU. So, in any case, don't do what I did because it's stupid. Pick one and live with it if you need it. Okay, and now this goes back to using those sound cards to measure audio. If you take one of those standard sound cards, any of the ones that I've shown there, or for example, Focusrite or one of the EMU USB cards, the problem is their input range doesn't match testing audio products. If you're just testing line level stuff, fine, but if you're actually testing an amplifier, it won't work. You'll break something. You can build a simple passive interface. It's finite, you know what it is, but you know, it's kind of kludgy. Both Pete Millette, which is the upper one, and Jan Didden's Auto Ranger address a number of issues. They have metering on the front, so you know what's coming in. No confusion about that. And in any of the sound card solutions, you have one really key challenge. The sound card won't tell you what the signal level is coming in. It won't tell you with any confidence that it's 10 volts or 30 volts or 100 volts. It just tells you relative to overload. You can go do a bunch of calibration on them, but it's probably better to take this approach. Both of those have metering that tells you what's coming in. They have differential inputs, and that allows you to measure the signal coming out of your amplifier without ground loops. A good differential thing will get rid of the fact that if you don't have it, all of the energy from the power supply or from the current going out the output gets pumped over the input. You get ground loops and other confusers that really degrade the quality of the measurement. You want that differential input. Jan's, well, this is a brand new thing that he did. Some of you have probably seen it if you've been following the stuff online. I have one in the next room. It works quite well. It automatically ranges the input. You don't even have to scale it. It tells you what the input is. It tells you what it's feeding into your sound card. It tells you the number of dB of correction. It has a differential input and a single-ended input, and it has a differential and single-ended output to interface to your sound card, which gives you a lot of flexibility. It will just work. It runs off of USB power. It uses his silent switcher, so it has very good low noise and good distortion performance. But you need a good power supply to run it. And that means you need to really use an external USB source. If you plug it into your computer's USB to run it, as I learned the hard way, you will get noise and common ground issues because the ground on that box and the ground on your computer will be shared. That's always a problem. That's why you need these things with the differential inputs. I believe he's just started shipping and some people have had them. I don't know if anybody else in the US has received one yet. None of you have seen it yet, have you? Okay. Then, this product's been around for a little over a year. It's a nice little self-contained, dedicated audio analyzer. What it will do, it has differential inputs, balanced outputs. It's good for up to 30 volts. It has an automatic attenuator, so if you feed it too much for the range it's at, it switches that in. It's useful, it works, the software is pretty good. I mean, it's a decent one-stop solution. It has its limitations, and you do have to learn how to use it like any of these. If you needed to get one box to go turn it on as a hobbyist and go make measurements, this is a really valid starting point. I think they're around $500 right now. How much?
5 minutes.
Okay. Then the RTX 6001. This is Jens Hansen's hobby project for the last 5 years, but the company is a very professional company that he's a major player within. So this is passing through their instrument building division. It's basically the highest performance sound card you're going to find. It has lower distortion, more output, more dynamic range. The input will handle up to 100 volts. The output will deliver 10 volts with a 100 ohm source, so it can drive, actually can drive a speaker for some measurement purposes. It'll drive pretty much anything you need to test. It's a significantly more expensive solution, and it doesn't come with software. It is literally a sound card. But it does have software control on the input levels and the output levels. So you can go scale it, and then you can work with your software. And I think some of the people who write some of the software are starting to look at integrating that information into their software so they can do intelligent scaling. I hope so, because that would make it very useful. These things are around $1,000, except they're going to get more expensive after this first group buy. And then we have his product.
I'll just hold this because I'm going to give it right back to him after this slide. So I work now for a company called Avrometrics. We're a startup, but we've been around 5 years. We were mostly selling production line test equipment for, like bed and nails testers. Our customers are mostly in China. We have this new analyzer. It's right here. It weighs about 5 pounds, so it's fairly portable. What's unique about it in this price point is that it's both analog and digital, and it's Mac or PC. And the other thing is we don't use a USB connection. We use a LAN connection. So that means you can leave it sitting on your bench at work, go home, and log in to your network and operate remotely. Thanks. And then we can expand it. So this is 2 channels, but we can go to 200 channels, no problem. We're still looking for the customer that needs 200 channels, but we can do that. And then we've got a front panel control, and we're running a little short on time, but maybe I can do this just quickly. So from the front, I'm an analog guy. So I'm an analog guy. I like knobs. And so from the front panel here, I can, it's not displaying, is it? Let's see, do we have that? Okay, so from the front panel here, I'm just going to say start looping this FFT. So I'm just running this FFT continuously, and then I can press a button on the front panel, and you see on the slide, I can choose a parameter to edit, and so right now I'm changing the frequency, and using a knob on the front panel. I'm not using a mouse, I'm not using a keyboard to change that frequency. And then I can say, you know what, I want to change the level. And I'm just going through a filter with some diodes in it to create distortion. So as I turn up that level, you can see the diodes start to conduct and all these harmonics. The idea is we know what people are like on the bench, and what we find is a lot of people have a laptop, they use it in their office, then they go to their bench and they precariously balance their laptop on something. They don't really want to use a mouse and a keyboard on the bench. So that's why we put a knob. We're going to assign lots of functions to the knob and make that programmable in future release. So anyhow, that's where we are right now. Oh, it's $3,000. So actually, yes. So I actually have a shipment that that is ready to go out to Amazon. We're selling on Amazon too, but Amazon takes a chunk of change, and so what I can do is hold off on that shipment. Anyone wants a 10% off discount, I just won't send out next week's shipment. I'll sell it to you guys. Works out better for you. Works out better for us too.
Yeah. Is there any kind of analog filter in the front end? Not notch filter or anything?
No, we're just, yeah, we're just.
Still need that externally.
What's that?
Don't you still need a notch filter externally?
No. So we do have a notch filter. We have something in the hardware. No, it's actually all in the DSP. It's all in the DSP. Yeah.
I mean, if you're measuring an amplifier that has extremely low distortion, you're probably going to need to notch out the fundamental, even with the.
So, you know, when you get into the high end, I think there's a slide on that. If we go back to the slides.
Yeah.
3K is high end.
When I was at AP, I saw a lot of stuff for $45,000. So, but yeah, their 555, which is their best unit, actually does do some stuff with an analog front end, and they have dual notch filters, one for each channel, and that's how they're getting -120 typical across the band and stuff like that. So there is a compromise there, absolutely, but these days the converters are pretty good.
Okay, where are we?
There we go.
Okay. Okay, and then here we talk a little bit more about the state of the art. And the APX 555, commercial product, you can buy it. It can hit what is this almost magical number of 120 dB THD plus N. That means the noise is really low and the harmonics are largely non-existent. That is good enough to test all but the most exotic electronic design. There's pretty much nothing made that can't really find the problems with. But it's expensive, and really to use it, you're not spending just $29K. Okay, now here we jump to the other end of the universe. Some of you have heard about Victor's little oscillator boards. They are pretty much as good as the APX 555 as a source. They're fixed frequency, but they're $60 or so right now. The poor guy is building them in the evening somewhere in Eastern Europe, but he does an exceptionally good job. I've been extremely pleased with them, and they're very reasonable. There's actually been a bunch of activity around them. Somebody's designed a complete package where you can take them, put them inside of this other package with batteries to run them, and there are a whole lot of good reasons to do that. It's definitely the best value you're going to find. David Barber has built an oscillator, a fully tunable oscillator. It's another DIY project. Hopefully he'll move to the point where he will start sharing them. It is computer controlled too. He has a whole USB interface, which is a nice thing. And then the most exotic thing out there are these Radiometer Copenhagen boxes that are designed to measure the distortion generated by like a pure resistor. The one I have actually has a residual of -170 dB on the third harmonic, which is absurdly low. But you really can put if you put a mica cap on there, it'll show you that its distortion is 30 dB higher than a good polystyrene cap. It's a very useful gadget if you need to sort parts. There's nothing like them anywhere, and they're really hard to find.
Now, are those bottom three all just oscillators, or is
The radiometer is a complete, very specialized instrument. The other two are oscillators.
And the radiometer stands about that high, that wide.
It's huge. It's an amazing project given its history. Okay, load resistors. This is another thing. If you're going to go build and test amplifiers, you need to have a load to test it with. And I've watched people spin their wheels trying to chase down the most perfect load resistor, thinking it's going to make a big difference. I had to go get some load resistors for a test setup, and I have access to good ones, but I decided I am not going to spend that kind of money to get some load resistors until I've checked out some cheap solutions. So I found some nice inexpensive ones from China. But I wanted to go see, well, where do we stand? So the first thing, I took a sample. This is your typical 250 watt inductive load resistor, 8 ohms. This is the kind of thing you'd buy normally if you were setting up one of the fancy test systems. It's inductive. Well, geez, that's got to be no good. Well, the actual inductance is 1.6 microhenries. That's very low. This is measured at 150 kilohertz. As you can see, the resistance is increased. It's right at 1% high, not very much. Okay, so that's our inductive resistor. Well, here's the really telling thing. This is the inductance of 3 feet of wire to hook it up. You're already there at 1.4 microhenries. So if the resistor is less than that, it's not an issue. So don't chase down the very expensive non-inductive ones. At one point, I chased down some very fancy film non-inductive resistors, and they were all rated at 100 watts, and they all promptly fried. It was very frustrating. So, and 3 feet of wire, 100 milliohms. Again, not very much. So the combination here, if you put the two together, you end up with 3 microhenries. That's not going to degrade the meaning of any measurement you're going to make with this thing. It's not like the resistance at 50 kilohertz suddenly jumped up by 50% or even 10%. It's barely even 1% overall. And most people can't test amplifiers at 150 kilohertz because things like the Zobel networks start pouring out smoke. Been there. And then these are the resistors I found online, which turned out to work just about as well, and those are $1.50 each. So you can buy those, mount them on a heat sink, and you're pretty much ready. You don't have to spend a lot of money and hassle that. Now, if you want, and that's not enough power, what you do, the real classic trick is you find a bucket, fill it up with water, and dump it in. And then you can handle an amazing amount of power, and you warm up the room too. Okay. So, questions? Sure.
So there's this constant confusion of how to measure noise.
How to measure noise. Okay. Let me just sort of cover one larger sense here. This is a really thin overview. There's so many subtle details in this where you can get yourself trapped. Little things where you don't understand why you're getting what you're getting. Noise is a classic one. And especially if you look at an FFT of noise, it's very misleading unless you understand how this all works. A higher resolution FFT, suddenly your noise floor went down. And that's because what you're measuring is the noise in each little tiny bin. But when you actually measure the noise coming out with the classic sort of noise, A-weighted noise, it adds them all up and gives you the real number. Now, how you hear and how that relates to what you measure, this is where you got to go understand, learn, and decide what matters. There are several ways of doing the weighting, which is to adjust the noise measurement to match how intrusive it will be. The classic one is A-weighting. It's nice for some things. For electronics, actually, there's a thing, what's it called, the one that was hatched by Dolby?
CCIR.
Yeah, CCIR, something or other, essentially. Yeah, what it does is focus at 3 kilohertz. At low levels, your ear is most sensitive around the 3 kilohertz region. So noise there is still intrusive even if it's pretty low. So they did a weighting at 100 hertz. It's like 20 dB higher than it would be at 3 kilohertz. And that would be a reasonable reflection. Hum, you don't hear hum too much until it's really loud. This high-pitched noise, you will hear it even as very low level. The classic example of how important that is if you're in a concert hall and they're playing quietly and somebody opens a candy wrapper. That's not very much energy in a hall with 1,000 people, and you hear it all through the hall. And this is indicative of the way our hearing works and how sensitive it is to these very small noises. So,
And the other thing too about noise, there's steady noise, which your ear actually filters out pretty well. You can be in a room with a hum of a fan. And
like in here.
Yeah, right, you don't hear it for a while. But there are devices that pump noise. The noise level actually changes. It could be because of a DSP algorithm. Sometimes it's the converters themselves at different voltage levels. The noise floor changes, or as they change between voltage levels, the noise.
Or you have a fan that changes speed constantly.
Yeah.
You hear that.
Yeah. So understanding how noise impacts you and impacts your enjoyment, you can actually listen to some very old recordings that are fairly noisy, and you can still go, wow, that's an amazing recording, because that noise is steady throughout the recording. But if that noise keeps changing, you're going to be, oh, wow, that's terrible, because you're going to notice it.
Yes?
So going back to the amplifier test limits,
Yeah.
I'm seeing amplifiers, switching amplifiers that are specified using a resistor in series with an inductor, and there seems to be like a de facto industry standard of about 33 microhenries in series with, 4 or 8 ohms.
Oh, that's somebody dodging reality.
Yeah, so can you comment on that versus like just...
Well, if you're trying to emulate a speaker, yes, it makes sense to have a resistive and inductive, because the speakers are inductive as well as resistive. And if you want to see what's going to happen, and particularly with a switching amplifier, depending upon the design, you could actually run into instability with an inductive load, with the feedback and the nature of the way they work. So it would make sense to do that. But if you're going to just measure the power output, I don't know why you'd do that unless you're just trying to dodge something.
Well, there's another thing with measuring Class D. If you have an analog detector type of analyzer, you've only got about 40 dB range on the detector. You have very high level spiky noise out, at some multiple, either at the fundamental or some multiple of the fundamental. That can take an op amp and make it go nonlinear. Basically, the op amp
It clips internally.
Well, slew rate limits.
Yeah.
And so that's why you saw with the old APs, they sell you this $1,000 filter, which a bunch of air core inductors, custom air core inductors, they're really good at the pass band. I think is like a less than like a 1/10 of a dB ripple.
It's really low and
then
no
it starts
distortion.
rolling off, and they make two versions. One rolls off at 25, and one that rolls off at 40. So for you can do wideband stuff. And with the DSP analyzers, like the APX systems, I generally found that most of them are relatively insensitive. Your converters have over 100 dB of dynamic range, and so in the presence of that noise, also the newer designs have faster op amps. If they have an op amp on the front end, usually they do. It's usually some sort of instrumentation amp, but so they're less susceptible. But that's something to be aware of.
Yeah.
During Class D with older analyzers.
Oh yeah, that's a very important thing to keep in mind, because they will have as much as an almost full scale at 200 kilohertz to 500 kilohertz on the output. You have two issues with them. One, this will go and, as he was saying, potentially limit the input, especially if it's an older unit using a 5534 op amp, which doesn't do well under those conditions. The other classic problem with one of those is how many FM stations it knocks out. And depending upon how loud you're playing, it's a different station.
For switching amps, usually the test load is specified to go after the output filter.
Yeah.
Which introduces some complications because output filters may be different for different amps. So
Oh, well, yeah. Well, it depends on what you're trying to do. If you're trying to design around one, it's one thing, and you have to really work through all of that. What you're using for an output filter, how you implement it, how you tune it, and what your intended load is. Typically today, the bulk of that business is inside of boxes. I mean, it's kind of crazy. Here we have people struggling with really complicated passive crossovers going to complicated speakers. Your typical $100 Bluetooth speaker has 3 or 4 amplifiers and a very sophisticated DSP crossover doing things you can't even do with those traditional analog solutions. There, each amplifier is very carefully tweaked to work with its target speaker. The whole thing is optimized. The amplifier costs about $1.50, and there's almost as much money in the passive components on the output of it to make it all work. But they're far more sophisticated than what we're doing in this high-end audiophile realm in that sense. Execution, though, I mean, if you're selling the speaker for $100, you have to be very efficient about your execution, and it's not necessarily premium, but the technology is way beyond what we're doing here. In any case, if you are designing around digital amplifiers, the bulk of your business is going to be this very closed loop where the amplifier and the speaker are dealt with as a system. And you'll have either the low-pass network, and there are some architectures that allow you to avoid the low-pass network, and they do a lot of tricks so you won't get too much of that FM interference or anything.
I just want to add, if you really want to get your mind blown, you should see what goes into the phones, and the speakers inside your phone, or the speakers inside a laptop computer. The integration, those amps actually current sense the speaker, and they know exactly how close the speaker is to its limit at all times. It corrects. Some of the most advanced amplifier technology is just for microspeakers. It hasn't made its way into the pro level yet.
Oh yeah, I mean they
But
can.
they're building it by the millions.
Yeah, they're designed to literally tell, are we about to burn up the voice coil, and they moderate it back, because the voice coils are fragile and you don't want it to break, but you got to push it pretty close to get any sound out of them.
I know, so they actually monitor the temperature of the,
Voice coil.
so, and they're making this called speaker protection.
Yeah, that's technology. TI calls it their smart amp, and they have this whole process for characterizing the voice coil, figuring out the temperature rise, and predicting it. It's pretty sophisticated, and it's something you can only execute with some sophisticated DSP, but it really does work. But it's, right now, they only have one chip that you can even use at 20 watts. Everything is way low power.
Well, there's another solution that, who was it? Eminence was selling it. It's something called Defend, and it was designed by this guy, Joel Butler. It actually senses the speaker load, and it actually clips the waveform, but in such a way it's like turning it off like a Class D amplifier.
Ooh.
Oh, we're out of time.
Yeah. Okay.
Thank you.
So, one more thing. We have these things on demo in the next room if you want to see them up close. Thank you.